Hello, I am Riley Troyer, and welcome to a quick summary of my poster. This poster is about a now NASA finest project to study the energy spectrum of pulsating aurora using the poker-flat incoherent scatter radar and the wave-particle interactions for pulsating aurora electrons using the Van Allen probes. Now, this poster will focus specifically on the energy spectrum analysis. Just as a bit of background, pulsating aurora, or diffuse-like aurora, although not diffuse aurora, that appears these widely varying dim patches of aurora that blink on and off with a variety of periods, which is typically between 2 and 20 seconds. Now, these aurora, the electrons responsible for these aurora are thought to originate in the outer Van Allen radiation belt from a wave-particle interaction with what's probably lower band chorus waves. The energy of those electrons is one thing that really distinguishes pulsating aurora from other auroral types. They can typically be almost an order of magnitude larger and ranging between about 10 keV and hundreds of keV. From basic physics, we know that higher energy particles will reach further into the atmosphere. And the left figure here I've just plotted, this is a basic formula, is just how far we'd expect different energy particles to penetrate into the atmosphere. Now, knowing the atmospheric density, we can actually figure out the amount of energy a particle will deposit into the atmosphere as it makes its way down. Now, I've plotted this on the right for a few different particle energies. And from this, we can see that obviously the larger energy electrons will deposit more energy at a lower altitude, meaning that they're more likely to have a larger effect on the atmosphere. Therefore, these higher energy electron events, as pulsating aurora, are important to study. Now, the way we're studying this is with the poker-flat incoherent scatter radar, which is basically this giant radar array that fires a beam up into the atmosphere. It measures the backscatter. From that backscatter, it gets a variety of parameters, but the one we're interested in is the electron density. I've plotted the electron density for a specific event on the left figure as a function of both time and altitude. And you can see right at that start of pulsating aurora, marked with the red line, you get this increase in density at lower altitudes, indicating that high energy particles are precipitating into the atmosphere. Now, if we take this data and average it for periods of different types of aurora on this night, you get the figure on the right, where we can really see how different pulsating aurora is to other types of aurora, where pulsating aurora is this blue bottom line, where the peak in that density is significantly lower, indicating again that higher energy particles are precipitating at these times. So using that data and doing some calculations, our analysis models the energy distribution of those incoming electrons. And you can see from this that the pulsating aurora picks out the pulsating aurora as having significantly higher fluxes at these higher energies compared to other types of aurora. Now, you should take the actual numbers of this plot with a grain of salt, as this analysis is still a work in progress. But going forward, we're planning to really hash out this analysis and run it for many more pulsating aurora events. Since the events we've looked at so far indicate that this ionization at or below 80 kilometers is very common with pulsating aurora, which corresponds to roughly up to 50 or higher keV electrons. So that was my quick summary of my poster. If you have any questions or want to reach out, please feel free to either leave me an email or send a message through the contact author button. Thanks so much.